Hello, I'm Martino, founder and CEO of Kadena. First, I want to say thank you to Erica and everyone else here who put on BUIDL. This is a fantastic conference, and they brought together some really good teams. Before we start, I want to give a touch of background to have kind of a good context of where Kadena and the project that was built is coming from. So I got into crypto in probably one of the strangest ways that may be even possible. I was actually at the Securities and Exchange Commission in the United States and was there when Valerie formed the cryptocurrency working group. They needed a tech lead to come in when she founded it who didn't own any coin but could help the regulators and the lawyers to understand the technology to go and help to think about what we should be doing with this. From there, I went to JP Morgan, where I'm my co-founder, and we built their first international private blockchain called Juno, which was open sourced and deployed in around 2016. This is out of the same group that did Quorum thereafter. And after deploying this blockchain, my co-founder and I left and founded Kadena. When we were there, we came up with all these questions that needed to get answered because the reality of blockchain is quite different from its promise. Public blockchains are too slow and too congested. You have a killer app that goes onto the chain and it clogs the network for days. Private blockchains we don't have a way to really scale them or get the throughput that we need when we go to larger scales. Smart contracts have an enormous amount of promise, but are complex and unsafe. We've seen hundreds of millions of dollars be lost because of bugs. And general purpose languages are just not suited to protecting the type of value that we hope to represent with these systems. So our solution is a very different approach. While I don't think that one chain is ever going to rule them all, I do think that there's going to be standardization at the smart contract level, much like we saw with SQL and databases back in the 80s and 90s. So for that, we have Pact, which is an embedded, accessible smart contract language, which we'll get into in a little bit. And that runs on top of, it has the ability to run on top of multiple different systems. One of which is Scalability, which is our private blockchain. You can think of it like a sidechain or a enterprise blockchain. Kadena is a bit unique in that we already have Fortune 500 clients using our enterprise stack. We've had them for over a year, and we're picking up new clients every quarter. And soon we're going to be launching Chainweb, which is a very different approach to scaling a public network. It uses proof of work, but it braids it in a way that allows you to keep the energies the same, but to drastically increase the overall throughput and security of the system. Now, Pact is interesting because you can put it on top of different things, and really, we should really want to use smart contracts everywhere because they should be able to just be so ironclad and be so safe and so easy to use that it's a type of system we should want to be using all the time. But that isn't the case today. So we're a bit different because of our enterprise heritage and expanding out. We have a holistic stack that is aimed at, it's built for entrepreneurs, but it is ready for enterprise adoption. We did that because enterprise gave us discipline, because we could focus on business use cases and business adoption and doing real work on these systems without having to worry about token speculation early on. And then by being proof of work, it just makes it a very different approach. So Chainweb, our consensus protocol. Chainweb, to a certain extent, breaks down the trilemma. It has a very weird property in that as you increase its throughput, you also increase its security and increase some notion of decentralization. It depends on what your exact definition is. It isn't a completely new idea, but it is a further extension and generalization of something that was proposed 4 or 5 years ago by, I think it was Blockstream. So, brief overview of proof of work. This is the reason that we're all here today. It's not the mode of consensus. When it was first proposed, I didn't know if it actually would work. When you have a consensus algorithm and you fuse economics into it, you need to battle test these things. You can't actually formally prove it with game theory or anything else. You need to put it into the world and see what happens. So, proof of work, standard, miners race to, can't see this at all. Miners race to form and mine the next block. Every block points to the previous block in the chain. The longest chain wins. We should all know exactly how this works. Now let's generalize it a little bit. Instead of there being one chain with one ledger, Let's partition it into two. Every time you make a new block, it points at its previous block and that of the other chain. You can't advance one chain, in this case, beyond the other more than one block, because you need the Merkle root of the other block to form a new block for your chain. Now this allows you to double the throughput. But in the process of going from 1 to 2 chains, you take the mining difficulty and you cut it by half. You take the block reward and you cut it by half per block. Over the entire network, the energy use is more or less the same, because almost all of the energy and the resources and the money used to actually run these systems is being consumed by the mining itself. And by chopping the difficulty in half, you keep the hashing the same. Now, there's a little bit more that goes into replicating each chain, because now you have to have 2 replicating servers, but the cost is pretty low. Miners are going to be into this idea, and they already are. The problem is that you can't take this idea very far. When you have, say, 10 or 20 chains that are all referencing each other's previous block when a new block is formed, that means the network needs to come to consensus around the entire last layer, which is what our term for block height, the entire last layer of blocks. It won't work. And that's where we generalize it. We inject graph theory into the way that you braid these chains. And it's worth noting that these chains, that this graph, they aren't validators. Instead of having a single chain that is ownerless and trustless like Bitcoin or Ethereum, in this case, you have 2. All the miners are replicating both chains they're both working on and distributing their hash rate across each other. So we take this up to, let's say, 20. If you go from 2 to 20, you chop the difficulty by a 10th, the reward by a 10th. You need 18 more servers or 18 more replicating nodes, probably more servers to do it, which is a relatively speaking small cost. But at this point, you have 20x the throughput of a single chain. By having this cone structure that you can see, we call it a Merkle cone because it looks a lot like a light cone that you see in relativity, but we didn't really have a good analog to use to define it. You actually get much higher security as you increase the throughput. Because to do a double spend against that black block that you see, that block all the way back, you have to have in private you have to mine in private all of those blocks that could have referenced it or any of the other, or anything that referenced it. So these are direct and indirect references. And the key here is that it's proof of work. You already have to wait a few blocks for confirmation. So instead of using, if you have a background in Ghost protocol that Ethereum uses, where you have a block and then you have some uncles, instead of just using those to increase the security, thereby decreasing the confirmation time, we're using those to refer to other blocks in parallel chains that represent other throughput. So they aren't just for security at this point, they're actually for adding throughput. One way to think of it is that we are multiplexing the hash rate. We're squeezing more information through it, but keeping the overall size of it the same. Every chain mines the same fungible type of token. Now these chains are sandboxed, so you can have accounts on multiple chains, and actually you have to. Having an account on one chain in the network doesn't mean you have an account on others. And simple proof of burn is used to transfer coins from one chain to another. Now, in the burning process, all of the infrastructure for that is all in the smart contract layer, which means that you can also do great things like load balance smart contracts. So you can deploy CryptoKitties to one chain, have amazing market, and then saturate that chain. The rest of the network doesn't get congested, but that one chain does. And then seeing the adoption taking hold and running away, you can go and deploy other contracts or the same contract to other chains, and then start load balancing between them. So instead of it running on one chain with, say, 10 transactions per second of throughput, you can deploy it to 4 chains, and now 40 transactions per second of throughput. All without having to fundamentally change the protocol of the approach or go to side chains or anything else. And now we get to the real killer app of the platform, which is Pact, or smart contract language. It takes a very different approach, so it's going to take a little bit of time to explain. So smart contract needs, they're all about authorization, database operations, and the logic that lives between the two. When we were at JP Morgan, we tried to actually my co-founder and I, we tried to get Ethereum to really work for enterprise. It was designed for public, which made a migration to enterprise quite difficult because enterprise workflows and business use cases have different needs. One of the ones that we knew right off the bat that we would need is the ability to safely upgrade contracts. If we walked into the executive of a trading desk and said, let's use blockchain for your business line, but then said, oh, by the way, if there's a bug, we're going to need to hard fork the protocol, the actual client code, to affect that change, we would have gotten laughed out of the room. Now, smart contracts also should be, they need to be incredibly safe, so they need to be easy to use. And one of the best ways to approach those needs is by decreasing the surface area for attacks. So limiting and constraining the language to the work that you need to do, but not anymore. By reducing the overall difficulty and by making the language very clear and easy to understand, it makes it harder for bugs to seep in. There's just less places for it to hide. And going Ethereum early, the EVM Solidity showed amazing promise, but the approach that it's taken it has some problems. The compiled code means that we actually don't know the code that is being executed, like the source code for what's being executed on chain. There's no guarantee you'll be able to find it. Compilation necessarily means that you're taking more information and you give the compiler more information, and then it optimizes the actual execution, the binary that gets run, but some information gets dropped because it knows more about what's supposed to be going on. You can't always go backwards. Also, by it being a general purpose language, it means that you have issues like reentrancy, which the DAO had happened to it, or you have just bugs can lurk in places where you don't even really need the capacity, so loops and recursion. Pact is a Turing incomplete language for a reason, and it's a safety feature. Because from my point of view, the place that bugs hide the most and the most often is in recursion and in looping. It's the hardest part of being a programmer is thinking about how state builds up in your head. So there's a number of things to cover here. For one, it's an interpreted embedded language, which means that we're not putting a CPU onto our blockchain, we're putting an interpreter. We're embedding the language into it. The code that you write, which you see here, is the code that goes on chain, is the code that gets executed. Pact was designed by our enterprise roots and our business adoption matters roots. We focused on this idea that that non-engineers, that technical domain experts, like lawyers and executives, need to be able to read, if not write, the code itself. This is in the same mantra as Excel or as SEOUL. We all know people who are amazing at Excel but don't consider themselves real programmers. And we all know people that, the advertiser that learns SQL but isn't really, a mainline developer, either front or back end. These things should be approachable. By making it easy enough for an executive to understand and to use, you actually make it very easy for an engineer to use, and you make it safer at the same time. It's this great confluence of events. It is Turing incomplete. This drastically reduces the attack surface and makes what we're going to talk about in a few slides, formal verification, much, much easier. It's a single assignment language, so you can't have just variables changing out from under you. Anyone who's used JavaScript knows the pains of this. So Pact is designed around this idea that there are kind of three sub-languages in this domain-specific language. One is an authorization language, which you see on the first line. This is a way of describing the capability-based security model that we have. Much in the way that Bitcoin script was designed around figuring out the authorization, we have a little sub-language for it. Multisig is a native. You actually have to make a singleton set. So multisig is the default for Pact. If you want to have a single signer for something, you have a set with just one key in it. It's not even code that you write. It's not like in Ethereum where you have to actually code a multisig contract. Then you have code and data. So we have a SQL key value data store metaphor baked into the language. You can see that in with read and in write and the last two lines, and also create table. This key value database metaphor is, it has the ability to link up with multiple different backends. Again, because of our business adoption matters background, it has the ability to link over ODBC to arbitrary backends. For the public network, it'll run on its own cryptographic data store, but you'll also be able to run a full node that's going into, let's say you have a newer system like a Postgres or a MongoDB. Let's say you have an older system like we saw at JP Morgan. It could hook up to a DB2 or even potentially an IBM mainframe, because you're going to need to integrate these systems when they take off with existing back-end architectures. On top of that, we have coroutines, so these are multi-step functions. They're called packs. It allows for a very easy way of describing escrow and also the capabilities around advancing the transactions. Those aren't actually seen in here. And the main thing is that it's human readable. This language is really meant to be understandable, and that's whether it's by executives, by lawyers, or by engineers. So when Ethereum was first proposed, it had two major features that it was going to bring to market. One was being able to issue tokens. It totally nailed that. It's one of the main reasons we're here today. The second one was supposed to be contract interoperability. That one hasn't been successful. And you could have kind of seen it coming because von Neumann architectures have this problem. The best example of it is parity multisig, where instead of everyone having their own lump of code that represented the multisig wallet and putting all of that on chain, there was a main contract that other people were importing from. And that main contract got poked in the wrong place. It blew up, and a bunch of money is still locked up. I think at the peak it was something like 200 million was locked up because this one contract had died. Now, to solve the interop problem for smart contracts, you need to do several things. One of them is have real governance. So in Pact, when you make a smart contract, you say hello, or like the name of it is hello in this case. And then the second thing that you put when you make a smart contract and you give it a name is the way that it is governed. Because you shouldn't have to hard fork a network that fixes a smart contract. You should be able to describe whatever governance mechanism you want for that code. It's maybe a little bit anarchist of me, but I don't think that you should have to take into account the rest of the community just to upgrade the one contract that you and a few other people are using on the network. So if once you have governance, then you also need this other feature, which is snapshotting your inline. So when you import a contract, it actually takes a copy of the code and pulls it into your contract at instantiation. This is all in the environment. When you actually put a contract on chain, it's making a copy of this. So that if the copy underneath shuts down or breaks or something, the code that you put on chain is the code that is there. No one can come in and change the code out from underneath. There's more to how this works and how it interacts with databases and the protections therein, but we don't quite have enough time to dive into it too much. And now we get to formal verification. So because we have this domain-specific language that is Turing incomplete and that has a lot of really native functionality, or native functions, we're able to very uniquely be, I think, the first people to offer user code formal verification. Now, the theme for how this works actually is a continuation on the idea that a lawyer or an executive needs to be able to understand and read the code, because we have another DSL buried inside the Pact, which is our property defining system. This system allows you to have templates of proofs that can be automatically generated against your code. So when you use the formal verification system, you tell it to basically take your code, convert it into Z3, which is generalized Boolean algebra, and then you can give it a few of these templates, and it'll collect a bunch of metadata, make the proof for you, and then run it in Z3 and find the bug for you. It's an incredible thing to use. Now, it doesn't cover everything, of course, so if there are parts of it that you don't have, that you need to prove that aren't quite, that aren't built into this DSL, then you can go and actually jump into Z3 and use it directly, or you can jump into SPV or the subsystem that we have. But you shouldn't have to immediately. The idea is that over time we can build up enough of this DSL that you don't need to actually be touching the hard formal verification system all that much. Pact testnet is live. You can go to pact.kadena.io, now play around with it, deploy apps, show it to your friends. Pact resources, we are just beginning to internationalize all of our documentation. If you'd like to help, we would be happy to have your assistance on that. The language reference and white papers that are available in Korean are linked to here. And testnet has been launched. We have 3 different parts of testnet, 2 of which are already good to go and up and running, 1 of which is launching in January, and that is Pact on top of Chainweb. And our mainnet launch is aimed at Q2 of 2019, probably early summer. It's going to have a lot of different features that we're still building out today. We are pushing very hard towards mainnet launch, and would love to work with anyone here who wants to help out to really kind of advance the state of the art of smart contracts especially. Thank you. We don't have time for questions. One? I can't see it actually, so someone just...
So, as I understand, each individual chains in that complex graph consisting of the multiple chains only proves the others SPV proof.
So they are referring to each other's Merkle roots. When you make a block, let's say it's two chains, if you make a new block for chain A, it refers to the previous block of chain A and the block of the same height of chain B. Then that graph can allow it to expand out. The inclusion doesn't include any of the validity proof that the other chain is valid and doesn't have a bad block. That comes at the economic level, much like how proof of work doesn't have bad blocks because, or Bitcoin, you don't have a bad block because miners will try to validate a mined block, find that it's invalid, and then not work on it. The same idea applies here. It does assume that miners are going to be acting in a somewhat rational economic way, which is to be mining the entire network. For moving coins across chain, that's actually all at the user level, it's all at the transaction level. This is how one of the ways we get around the n-squared problem when you try to scale out one of these networks. I think that's it. All right. Thank you.